So when you write a parametric description of the solution set, it means that if you have free variables, you write the basic variables in terms of the free variables. That's what we did last time. You just call that a parametric description. You could write a different parametric description based on basic variables, but it's just convention. We're always going to write the basic variables in terms of the free variables. Okay, we're just always going to do that by convention. Okay, so we're all doing the same thing. Right. So what that means is you solve a system and you come up with this solution. You have this free variable x3, right? You're going to write x1 and x2 in terms of x3. This means solve the equations in terms of the basic, or in terms of the free variables for the basic variables. And then for the free variables, you can say they're free, or you can just say the free variable is equal to itself. So that's called a parametric description of the solutions. Have you guys had parametric equations at some point? Yes, no? Calc 2 or Calc 3, maybe trig. Might have done it in trig class. So, you know, you have variables x and y, then you have this other variable t maybe for time. That's a parametric equation, right? So that's what we have here. We have x1, x2, that's like x and y, and then we have this other variable x3, that could be your time component or something else. So it's that's why it's called a parametric description. So we would change x1 and x2 in terms of the free variables, and you can also introduce a substitute variable. If you want to say x3 is t, or s, or r, or some other variable name, you can give it a different variable name. So it doesn't really matter which way. They're both really the same thing. Okay, but you will see it in both ways. Okay. So if you have a free variable, sometimes you'll assign another variable for it, like t or something like that. Okay, and then it gives it that parametric equation feel to it. All right, so this is called Theorem 2, Existence and Uniqueness Theorem. That won't be the last time you see that term, existence and uniqueness. Existence is it there? And uniqueness is it the only one? Okay, so we're worried about those two things. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. What does that mean? So when you have you reduce everything, right? And if you come up with a row of zeros and the first non-zero entry is here, then you get no solution, right? And that would end up being a pivot column if you were to continue your row reduction, right? If it's not augmented, you keep going all the way. If it's augmented and that last column ends up being a pivot column, then you have no solution. Because that would mean this entry would be the first non-zero entry of that row. And if this is non-zero, like 2 or something else, then you get no solution. Okay? So that's what this means. So I've got a row that has all zeros until the very end, and that guy's not zero. So that means no solution. So a linear system is consistent, means it has a solution, if and only if the rightmost column of the augmented matrix is not a pivot column, i.e. if and only if an echelon form of the augmented matrix has no row at this form. All zeros, some non-zero number at the end. Okay, and it's augmented, right? If a linear system is consistent, then the solution contains either a unique solution. In such case, there will be no free variables. Okay, so if it's consistent first, and you have no free variables, then you're going to have unique solutions. And if you have free variables, you will have infinitely many, because you can assign literally any number to those free variables, and you'll come up with solutions. So it generates infinitely many. So that's unique, existence and uniqueness. Is there a solution? And how many do you have if there is one? So how do you solve a system using row reduction? Augment the matrix, use the row reduction algorithm. So you just row reduce your matrix all the way to reducer echelon form. Write the system of equations based on the new matrix, the new reduced matrix, and then rewrite each non-zero equation so that its basic variable is expressed in terms of any free variables. So augment your system in a matrix, row reduce it to RREF, rewrite your system with variables instead of in a matrix, and then you solve for those basic variables in terms of the free variables if you have free variables. Okay. So let's do it here. So I have two equations. How many variables? Three. The only two options I have here are no solution or infinitely many, right? We can't have a unique solution here because I'm going to have at least one free variable if I don't have an inconsistency. So I'm going to augment first in a matrix system, coefficients, I have this one top left corner. This entry here is already a 0, so I don't have to pivot. Then I have my leading 1 in this position. That's what I want. And I want to eliminate this -3. I want to make that -3 a 0. So I'm going to replace which row? Replace row 1. What with? Row 1 plus 3 row 2. Correct? You can write that different ways. Okay. Row 2, I'm going to keep the same. So 1 plus 0 is still 1. That's why it's important to make that entry a 0 first. Okay. -3 plus 3, 0. -5 plus -3, -8. 0 plus -3, -3. It's like that. So every row has a leading 1. Every other entry in the columns with leading 1s have 0s in there, right? So I've made this a 0, that a 0. My leading 1s are staggered. I don't have a row of 0s to worry about. So this is an RREF. This is completely done. Okay? That's completely reduced. These other columns, I can't do anything with them as far as reducing the matrix. Every row has its leading 1, and the leading 1s columns are taken care of. So now I rewrite the system. So the first row says x1 minus 8x3 equals negative 3. And equation 2 says x2 minus x3 equals negative 1. These two columns are pivot columns that have leading ones in them. Do I have a free variable? Yes. The third column does not have a leading one. It's free. So x3 is a free variable. Remember, the columns correspond to the coefficients of these three variables, so they correspond to those three variables. So to write my solution, I want to know the solution for all three of these. That's my goal. That's what I'm trying to solve for. Okay? x3 is free. I just like to say it's equal to itself, or you could say it's free. Either one's okay. The other two, I'm going to use these two equations. I'm going to solve them for x1 and x2 in terms of that free variable. So I'm going to move this negative 8x3 to the right side. Okay. So I'm going to say this is 8x3 minus 3. Same thing for the second equation, x3 minus 1, just like that. And if you want to make it look prettier, I guess, you could say, well, I'm going to let x3 be the variable t. And then this would be 8t minus 3, and this would be t minus 1. Both of those are correct. Any letter, except x1 or x2. Can't pick those because they're already used. So that's the general solution, and it's written in this parametric description form. Okay. Okay, that's 1.2. Row reduction. So let's go to 1.3. It's about vector equations. So we're going to do a little review on what a vector is. You've learned about vectors in trig, possibly calculus 1, 2, or 3 if you've taken any of those, or your physics classes or engineering classes. You definitely talk about vectors. Everybody writes vectors in a different way. Okay? So what a vector is it's something that has direction and magnitude, and we like to graph them so that the end point of the vector is at the origin, and we will draw an arrow designating the direction, and the length of the arrow designates the magnitude of the vector. So if the end point right here is at the points A, B, where this is how far x direction, this is how far in the y direction, A and B, okay? Then you'll see the vector written this way, AB. So you've probably seen that before, okay? We're going to write it in a different way in this class. Yep.
So that A and B are like x and y. They're not like magnitude and direction.
No. No. It's just x, y coordinates. Yep. The magnitude and direction would be, this angle here would be the direction. and the length of the vector would be the magnitude. Okay. So you learn polar coordinates somewhere, maybe you'll get there this semester. You'll talk about polar coordinates. It's kind of similar, just gives you magnitude, direction. We're going to write these vectors like this. Or like this. Like it's a matrix. So this will be a matrix with 2 rows and 1 column. So we'll say this is a 2 by 1 matrix or a 2 by 1 vector. And this one has 1 row and 2 columns. This would be a 1 by 2 vector or matrix. And we're going to say that those are basically the same thing. So any matrix that has just 1 row or just 1 column, we're going to call it a vector as well. Okay, we're going to say it's a vector. So if you remember this symbol, what does that mean from your other math classes? It's a big R with a double line. It means all real numbers, right? So this is the same as, say, the interval negative infinity to infinity. You know, every real number on the number line. Okay, it's all real numbers. That's what this symbol means. We're going to add this super. It's not an exponent. It's a superscript 2. We'll say R2. R2 is a set of all vectors that have 2 entries, have 2 real entries. So the ones that I wrote here, these are in R2 because they have 2 entries. And I drew it in 2 dimensions. Okay. If it's a 3-dimensional vector, has 3 entries, we'll say it's R3. And if it's higher dimension, you can say R4, R5, or R100. Or in general, we can just say Rn. That would be any vector of size n. Yes?
So would like R2 be in a 2-dimensional plane?
Yep. R3 would be 3-dimensional space, and R4 can't graph it. But it's in R4 space. It just it is what it is. There's no graphical context to it. And R100 can't graph it. You can't even imagine what it would look like, right? Our brains just won't do it. Don't try too hard. You might hurt yourself. You can't go past R3 in terms of graphing things, right? So, and even R3 is difficult to graph unless you have software. So Rn is a set of all vectors with exactly n real number entries. So they're sets of vectors. They're sets that contain all of the vectors possible that are a particular size. Okay? 2 vectors are equal only if each corresponding entry is equal. So each corresponding entry has to be exactly the same or the vectors aren't equal. And anytime you have a 0 vector, it just means a vector where all the entries are 0 no matter what size. So every space, Rn, R2, R3, they all have a 0 vector. It's just a vector that has zeros in all the entries. And sometimes we'll write it as 0, and sometimes we will actually put the vector symbol on top of it. And sometimes we'll use like U and V. So this U might have these entries, right? So this would be the same as writing this. And we will say that is in R3. That's a member of the set of R3 vectors. So if it's got that vector symbol on top of it, it means it's a vector, not just a real number variable. Sometimes, if it's just understood that we're dealing with vectors, we won't write that symbol. I will try to write it every time unless I forget. In the book, and maybe in the notes, anytime a variable is in bold, if a letter is in bold, that means it's a vector. Okay. I can't write in bold on the board. So I will be writing the vector symbol when I can. Okay, but in the books, it's probably easier to type bold than it is to get that vector symbol on top of the letter. So that's probably why they always use bold. But just know that when you're reading, if you're like, this doesn't make sense, then just remember that if it's in bold, it means it's a vector, then it might make more sense. Okay. You can add two vectors as long as they're the exact same size. So you can add two R2 vectors together, you can add R3 vectors together, but you can't add an R2 vector to an R3 vector. And the way you add them is you just add the corresponding entries. So we have this plus sign. Okay, that's not normal plus sign, right? Normal addition is not about adding vectors, it's about adding real numbers, right? So we just have to know that that's a new operation that we're learning. It's vector addition, okay? That's what that symbol means, vector addition. And we have two vectors of the same size. We add the first entries and we add the second entries, and that creates our new vector. We get a new R2 vector out of it. It's very simple to do, right? But just know that it's a new thing, right? It's a new operation. And then you can multiply by a scalar. So what is a scalar? A scalar is just a constant or a real number. A scalar is like just a real number constant. So scalars would just be an R set of all real numbers. You know, it wouldn't be an R2 or R3. Okay. So we have vector W. Notice that W is in bold. So that's a vector. And we have a constant, C. That's our scalar. And C times W is 5 times the vector. You're going to multiply each entry by that constant to get the new vector. Yes?
Can't you multiply a vector by a vector?
You can. We won't get there today. But you can. If they're written in a particular way and they're the right size, you can do it. So you just multiply. It's like you're distributing, right? But it's not the same thing. But you multiply the scalar times each entry and you get a new vector. Any questions? Yeah.
Yes. So with a lot of your physics classes and engineering classes, you get the magnitude and an angle. Could you sub in the angle, say, for your y coordinates in that? Or how would you go about that?
You would be using a different coordinate system,
Okay.
so it wouldn't work the same.
Okay. I'm just asking.
We're using vectors in rectangular coordinates.
Okay.
If you have other coordinate systems, you'd have to have a whole other system for doing your operations. So the vectors here are XY coordinate system vectors, and you can change them to magnitude and angle, but the operations don't work the same.
Okay.
Does that make sense?
Yes, sir.
Okay. Okay. So geometric description in R2. So what is vector addition in R2? So we have these two vectors, U and V. Notice they're in bold. Okay. So U plus V is just the sum of these entries. That's what we got in our example. So we want to graph these. Let's see, do I have a graph? I don't. That's okay. So let's see if I can graph this accurately. Probably not. Probably won't get this exactly right, but we'll try. So let's graph U. So U is 1, negative 2. So 1, negative 2 would be here, like that. So that would be U. Vector U. V is 2, 4. So let me use a different color here. 2, 4, like this. So that's V. And then U plus V is 3, 2. So let's do that in red. 3,